Hey guys, welcome to another video on data analysis in cosmology. Today we are going to deal with Pantheon plus data, and we will see that how we can fit our model with the Pantheon data. Now in the Pantheon data we have 1701 data sets, and it is carrying some supernova data as well as some SOOS data. All right, so in this video we are going to see in the detail that how we can do coding, what is the methodology that we are going to do in order to fit our model with the cosmological data. So let's get started. So our first job is that how we can build our model, or basically that as I'm taking the LambdaCDM as our benchmark model. So let us try to see that how we can construct LambdaCDM model so that we can actually fit with the cosmological data. So for that we have to first understand what are the basic structure, what is the basic theoretical structure, and the basic theoretical structure starts with a very simple thing, which is I guess over here, that which is FLRW metric. So first of all, our assumption is that the universe is homogeneous in isotropy and as well as flat. Now, if the universe is flat and homogeneous and all these things, then we can use this amount of metric, and then corresponding to it, we have some Einstein equation, or we can say that Friedmann equation, which is given by equation 1 and equation 2, where rho m is the energy density of the dark matter, rho dE is the dark energy density. All right, and the second Raychaudhuri equation becomes pressure of that matter and pressure of dark energy. Now when we are talking about the dark matter, it is evident that dark matter does not give you any pressure, so pressure is vanishing, so Pm is becoming 0. With this addition, we have the Bianchi identity. If you don't know, we have a continuity of equation. It says that the energy momentum is conserved throughout the expansion of the universe. So we have this set of equation, rho m dot, this represents as d rho by dt. So whenever you have quantity, this is basically this one. All right, so rho m dot plus 3h rho m is equal to 0, rho d dot plus 3h rho d plus pd is equal to 0. There are four basic equations with FLRW assumptions. All right, so now again, when we are talking about the supernovae has type 1a kind of supernova, so it has some absolute kind of brightness. So what astronomers is basically detecting is that they are trying to measure the brightness of that supernova, and then they are finding the corresponding distances, that what could be that distances. All right, and they have a very interesting thing. So in Pantheon data we don't have only supernovae, it also carries some Cepheid stars. So Cepheid stars have the brightness as well as it has some kind of a pulsating time. So when you have these two data sets, and from these two data sets you can easily find out that at what distance they are in, or what distance of galaxies that we are seeing. Because when you try to understand this Hubble parameter, it's basically telling you that how universe is expanding, or is this universe accelerating or not. All right, so in order to do that we have to understand that how far the galaxy is, or what is the distance between the galaxies, is this increasing or decreasing. Understood. So that's why we require some objects which has some kind of a constant quantity, so that we can measure it, and we can say that if we are going to look for another host galaxies, then we can conclude that okay, the universe is expanding or contracting based on the data that we have. So for that we have defined the distance modulus, which is defined by mu is equal to 5 log of 10 dl in the megaparsec. All right, plus 25 plus m. So when we are subtracting mu minus m, m is the absolute brightness, so we are getting 5 log 10 dl plus 25, where dl is the luminosity distance, how luminous, at which distance we are actually seeing this luminosity. All right, so we can get the luminosity distance using the model, that if we understand the what is the expansion of the universe as z, then we can easily find out the luminosity distance. So basically what we are having is that m and the redshift, that okay, at what redshift that we are getting the light, and it has some stretching. We understand the components of the supernovae and how far it is stretching, then we can easily calculate. Using this model we can easily calculate at what distance it is basically aparting. Or in other words, let's suppose I have some kind of a model. From that model I know what is sg, and then I know from the experiments what is my z and what is the mu m. So if I know these two quantities, I can easily predict that what would be my z, or in another way, for any model there are some kind of a constant, so we can determine or we can constrain the constants. So dl is 1 plus g 3 into 10 to the 5 kilometer per second, which is the speed of light. So mind you that this speed of light is always in kilometer per second and 0 to z. All right, so now if this is clear, now the problem is that let us say I am talking about LambdaCDM model. So LambdaCDM model, the Hubble constant will becomes h0. This is the Hubble constant, and then several constant, for an example omega m0 and omega de over here. So omega de is basically 1 minus omega m0 using that the same equation. So over here, my assumption is that the equation of state is basically minus of 1. So if you just plug this h over here, you can easily find the dl. All right. So this is basically what you have to do. Theoretically, you have to do. But the problem is that, all right, so suppose I have a LambdaCDM model, but somebody is crazy enough to make some crazy model. All right, so I want to make some crazy models. How can I build it? One of the ways is that, okay, you cannot just choose that omega d is equal to -1. Who said that omega d has to be -1? Einstein predicted that there has to be some cosmological constant, and it came out that the equation of state of that cosmological constant is -1. But I don't know if it's correct or not, so we can say that omega d can vary. So for example, I want to make my model like omega kind of thing. Omega is still a constant, but I don't know from the data I want to predict it. One is possible. Another way is that you want to go beyond LambdaCDM model, and the way to do is that you can make your equation of a state is becoming z dependent. And when it becomes the z dependent, what will happen is that if you see this equation number 4, then pd is equal to minus of rho d, so rho d becomes constant. All right, so for LambdaCDM model it becomes constant, but it will no longer become constant because pd becomes omega of z into z. So when you will solve it, you have to again do the integral. All right, so there are a lot of integral. First of all, the integral in the luminosity distance, and secondly the integral will be on this omega dz. But I will let you know that how we can solve efficiently these integrals. So if you want to go beyond the LambdaCDM model, what you can do is that you can just say that, okay, I can have some structure of omega de in such a way that we have a CPL type of parameterization. We have this kind of parameterization. This is called the Bagla parameterization. Bagla and Padmanabhan has worked it out with this parameterization. Again, if p is equal to 1, this we have parameterization, and we have this kind of parameters omega d exponential type of parameterization. This is called also GZ cosmological model. Or we have different parameterization. For example, people have worked out a Pade parameterization, or you can make your own hypothetical type of parameterization. You can see that these equations, if z is equal to -1, z is equal to -1, it means that it will tell you the future state of the universe. So this is becoming infinity, and everything goes abrupt. So basically they are valid up to today, but they will not tell you anything about the future. So for that moment, you have to again go back to your scalar field models, and then you can just say that, okay, fine, I have kind of some solutions. What could be the scalar field that can behave like this? All right, so that is the goal. Similarly, over here they have some limitations, but when you're looking at the past, they have a very good, you can just say that they are beyond LambdaCDM model. But when you know the solution, you can just construct a scalar field, and you can say that maybe this is the scalar field is depicting some kind of dynamics. That's all. All right, but the problem is that when we have a lot of integral involved, all right, I don't want to do the integration, because if you are writing the code, or if you are trying to do any data analysis using anything, let us say I have a 1701 data sets. Now what happens is that at each time it will put z let us say 0.001, 0.002, 1700 times. Now in MCMC, as you have already seen in my previous video, that we have iterations and we have n workers. Means that for one iteration I have some kind of workers which is actually taking different things. So each and every time for different omega m0, it will evaluate the integral. It is a very hardest job if you will do it. Understood? And that's what make it so inefficient, because if you have done the integral in the numerical analysis, then you can follow the Euler method, or you have trapezoidal method. So what you can do, you can just define some kind of a stepping, and then in order to converge this, you can minimize the stepping so that your error also minimizes. So you can see that the computer is doing a lot of hard work, and therefore the big trick that I'm going to share with you is that convert whatever the ordinary differential equation you have into the dynamical system analysis. You see that I have already 4 equations. All right, these are the 4 equations. Along with it, we have these equations. Along with it, if I just modify my omega d, again this one. So in another words, I have a 6 equation in which 2 equations are already in the integral form. It is extremely hard business to do with these things. So the thing is that your MCMC will get extremely reduced. The speed will become extremely reduced, and you have to wait a lot of you have to wait for a lot of time. Understood? So the thing is that if you want to do it everything correctly, and top of the thing is that I want to say that you have to choose the initial conditions. Although in this business it is fine that you can just choose that omega rho m to be between 0 to something else and so on, because here you have chosen already omega m0. In certain case you can just easily find out the solution, but in general, again the problem with the initial conditions. So the better thing is that use the ordinary equations. Ordinary differential equations means that whenever you have some kind of dynamical equation, change into dynamical system stability analysis, and for that you have to first construct the autonomous equation. I'm going to tell you what do you mean by autonomous equation, and then try to remove all the integrals. For an example, try to remove the integrals from here, and also try to remove the integrals from here. So I'm giving you I have given you already the motivation of why I want to remove the integration, because in Python or whatever the language you will work on, the differential equations are much easier to solve than the integrals. All right, so it is computationally very stable. Now, in order to construct the autonomous equation, first of all, step one you have to do is that you have to define some set of independent or dimensionless variables. So you can just say that I am defining some fractional densities, which is omega m is kappa square rho m by 3h square. Kappa has 8 pi g, and which is having mass inverse. All right, so we got omega m to be a dimensionless quantity. Similarly, omega d, there are a lot of publications you can see, and you can also see on my description box. There I have worked on various scalar fields in terms of dynamic system stability. You can go check it out, and you can learn that how the dynamic system stability is basically working. So first, the job is that you have to choose some dynamical variables in such a way that it has to be dimensionless, and you have to close the whole system. All right, and then what you have to do is the step 2, you have to take the time derivative of these things. Understood? So you are using the time derivative of the dark energy component. Now you have to use these equations in order to construct this autonomous equation. Now the one of the important thing you have to remember is that I don't have to require to find omega d dot and omega m dot, because I have this Friedman equation, and it will automatically provide me that whatever is happening at certain path, because this will become 1 is equal to omega m plus omega d. So if I know the dynamics, I can just use this dynamics to find out what will happen to omega m. So one thing is, it is already an inbuilt kind of characteristic in the dynamic system analysis that it will automatically reduce your number of equations, and the initial condition will automatically considered. So it is more efficient in a way to do calculations in order to predict the system stability as well as do a lot of things. So that's why dynamic system stability is extremely powerful, and at the same time it is very efficient to write your code in terms of these things. Now again, I have taken the time derivative. You have to convert it in terms of z, because all the data sets are in the redshift. So I have used this kind of conversion, that a is equal to 1 by 1 plus z. This is the standard definition, and then you can just take a time derivative, and you found that the Hubble becomes minus z dot by 1 plus z. So you can see that d omega d by dz becomes 1 by 1 plus z, 3 omega d 1 plus omega d. Now omega d can be constant, maybe some kind of z dependent, and so on. We don't care. Now 2s dot by 3h squared, you will get this one, and now we have defined it that what is my 2z dot by h square. You can find it from here. Equation number right of the equation will give you that what is 2z over h square. Now how can I find it? How can I constrain my h0? Now in order to constrain your h0, you can again use the right of the equation and try to find out dh by dz. Now omega m here, for example, it is 0. That's why there is no any involvement of omega m. So just finding the dynamics of omega d, and it is as clear it is. And then what happens is that you can use, for example, H0 for initial conditions. So for H0 correspond, if you want to solve it, you have to find out H0. So there are two different parameters. Here you have omega t. So from this equation, you will find the omega t. And but in this omega t, you can also simultaneously solve it to find out what is your H. So from here, for different initial conditions, so this is your, you want to constrain the initial condition of this one. All right. So this is how, we think. If I want to compare, if you have any confusion, I want to compare it, that how you have got this solution. Omega m0 is coming from differential equation. Now same thing is I am doing it, that okay, I am defining, I have two initial condition. One initial condition omega d0 from here. All right, so omega de0, and if I know omega de0, I want to constrain it, I will immediately know what is my omega m0. And for this equation, I have h0, and I immediately know that how h is basically looking like. All right, and this initial condition will be evaluated at z is equal to 0, provided that omega m is equal to 0. Understood? So what are the equations? The equations are this equation as well as this equation, and with the two initial conditions that we need to constrain is omega d is 0 as well as s0. Now, once it is clear that we have this distance equation, the distance equation does tell you that dl is equal to 1 plus zc, 0 to z, 1 by hz. So this is the luminosity distance. Now we can take the derivative d by dz, and using just a little bit of manipulation, I know what is the differential equation of this integral. Because you have already studied in your class 12 that integral is the inverse of derivative, right? So I am using that technique, and the initial condition that, okay, you don't know what is the initial condition, you can just put z is equal to 0 over here. So 0 to 0, it's again becomes 0. So dl at 0 is 0. Now you can also say that you have already used the integral 0, but here nothing comes. Understood? So dl minus 0. All right, so you can see that initial condition dl at z is equal to 0 becomes 0. All right, so you have already, so this initial condition is fixed, that okay fine, I know what happens that z is equal to 0. What is unknown is my h0 and omega d is 0. Now these things, and with these things, how many equations we have? We have number one equation omega d, d omega d by dz. Another equation is ds by dz, and this equation. So I have three equations, two unknown initial conditions, and then one known initial condition for dl. All right. And later on, when people have already given the data sets, they have provided m, or they have also provided this mu, but I am talking about this m because you have to understand that in Pantheon data sets, if you try to constrain this mu, and you can just say that okay, my m is also, I want to vary this absolute magnitude, so that I want to see that okay, I want to constrain my h0 as well as m absolute magnitude, then it is not going to work, because again they are providing some kind of degeneracy, and in order to break the degeneracy, you have to use again different data sets in order to minimize the chi-square. All right, so it's better to use just only m, the absolute magnitude. Now the problem is that when we're talking about the chi-square, so chi-square is data I minus the theoretical data that you are getting from your model. For each I is equal to 1 to n is equal to 1701. All right, so you can just, it's kind of a matrix, so you are taking a transpose, and then they have already provided covariance matrix. Now this covariance matrix is different. This covariance matrix is having 17 by 17 dimension. All right, it is a square matrix and having 17 by 1701 by 1701 elements. All right, so it is basically it becomes a row matrix, so it has only how many columns it will have one row and n columns. It will having n into n dimension of a matrix, and again it becomes a column matrix which is having n row and one column. So in the end you will get just only one value, 1 cross 1. All right, so this is what we have to minimize, is that log of probability. When you do the log of probability, it is this minus 0.5 times chi-square. So this is what we have to minimize. So covariance matrices basically tell you that what is the correlation between different data corresponding to different ways you have measured it. So it just gives you the error between all these things. So you have used some different satellites, some photometric ways, so it is kind of list, and the data sets you have, I'm using is the m. So the thing is that this covariance matrix is not like, suppose somebody has given you m and then there is a error of this thing, error of data, so this is not a covariance matrix. All right, so it is just for the visualization purpose, but this is again m, and you want to study it using the covariance matrix that is already given. So I will let you know that what is the covariance matrix now. The problem is that now Python code, I have already set up my chi-square, my model and everything. Now I have to write the Python code. Now Python code, what I am going to say is a non-optimized code. Non-optimized means that I have not written yet. I have not written it in terms of Python. Already I have written it, but I am not going to show it. It's kind of homework that you can do. You can, I have already made a video on how to write a code in Python. All right. Because when you use the code, right, when you write the code in Python, it will immensely make your system extremely fast. So if you want to with the parallelization, sometimes the code will take you a lot of time. On the other hand, if you just optimize it, it will take just only a few minutes or few hours, and then you will get your result. All right, so that is the meaning of optimization and non-optimized. So the thing is that it will be pure Python code. Now, first of all, how we can get the data sets? Just search in Google that Pantheon plus data and you will arrive at this GitHub page, and you will go there and you have to use this Pantheon plus data sets, where you will just take M, and then there is a covariance matrix. Pantheon plus SUS and statistics. Sorry, all the systematics. All right, SUS, statistics as well as systematics. So this becomes a Pantheon sample, and this is the covariance matrix that is you have to use. And here you have Pantheon plus data, but only SUS stat only. So this is another covariance matrix. So better use this guy over here, but you can experiment with also this one. So this is your data file, and this is the covariance matrix file. You have to download it, and you can see that this is about 23 MBs, and this is maybe some kind of KBs. All right. So if you will see, look at the Pantheon plus data, it is 5-6 code. Here is the row. You have to remove that. Okay, I don't want this row. This is some kind of ID. So this is the ZSD. ZSD means that at what redshift corresponding to you will find the supernova or some other things. All right. So this is already given the ID. Second thing is that in the 9th column you will find this mu b. All right. So distance modulus, and then there is an error, which error you don't have to use. It's for the visualization purpose. Now you have absolute brightness, that is M, and over here there is a error in M. So what you have to do is that you have to use this column as well as this column. For the Z data, this one and this one, and then you are done. I will let you know that. Okay, so how we can use this data loading in Pantheon? You can just download it. You can just say that np load Pantheon plus SUS data, use columns, because I'm going to use column. This upper head I don't want to use it, so start from here. So this is 2. All right, so that's why I'm saying that okay, unpack is equal to true and skip rows 1. So first row I don't want to take, and over here you can see that 1 0, so it's start from 0, then 1 and 2. So I want to consider this second column, then 10th one, and then also I am for visualization purpose I have also obtained this mu error. All right, M error, sorry. And then when I have taken this one, so I want to make my own file, that okay, I want to write this whole data sets into that, so that I don't have to carry this whole time Pantheon plus SUS dot data set. So with open I have write my own name, Pantheon data dot slash M and so on, and it will give you this only 3 columns, 1 2 and 3 Z, and then we have this M and then M error, so that I can use for any purpose. All right, so this is done. Now for example, you have to you are using the analysis. So first of all you have to import the libraries. OS numpy matplotlib for the plot corner, it is not necessary right now. scpy for the quad, now I'm not doing integration, I don't require this one. Solve IVP, obviously I'm using ODE solver, therefore it requires interpret, because yes, when you do the ODE you have to interpolate it, so it is a requirement. Matplotlib, so I want to update everything in terms of latex. Multiprocessing, when we are writing in the code in Python, we use multiprocessing. I have this multiprocessing. EMCE for the MCMC analysis. TQDM for for showing the bar that how it will progress. Get distribution for plotting the corner plots. These are the corner plots. And then when I am importing my covariance matrix, I have to take an inverse. As you can already see over here, that I told you this is an inverse covariance matrix. So you don't have to always inverse it. You just import your covariance matrix once you have inversed it, and then you are done. All right, so we have using sciencepy, lineage, and then las for I'm going to use this library, and then from here I will inverse it. So first line of the covariance matrix, okay, this is my data file. import z data, mu m data, as well as I am importing covariance matrix. Now this matrix in the data file, when you will obtain, everything will be in one row. All right, so what you have to do, you have to make it as a matrix. So I'm going to use reshape, because there are 17O file and 17O file, and this will be give you covariance matrix. And then you can again take the inverse of covariance matrix, LA dot inverse, and then co-matrix. Now this line is actually very stable, that's why I'm using this LA dot inverse. So science PY is giving you an amazing way to inverse the bigger matrix. All right, once it is done, now I'm going to define a model. Now omega d is for omega d, like I can have any crazy kind of equation you can give me. I am not afraid. I have already defined comment of kind of function. There are, now we have equation d, equation h, equation dl, and I have already defined dot h. It is just kind of equation. I'm just using dot h over here. I don't want to repeat myself many times, so I've just defined it. So this is dh by dz, this is d omega d by dz, and this is d by dz. So for that, you have to first define your redshift at which you are going to, this is the time variable or z variable. Now this is the variable, that what are the variables, like I have h, omega d, and d. So I have said that od, h, and dl are my variables, and then my parameters. What are my parameters? Od0 I want to constrain, h0 I want to constrain, omega h0 omega 0 is my constraint. These are the parameters, and so therefore return my this one, eqd, eqs, and eqdl. So I have defined this one. Now you can just say that, okay, eos will become omega 0 over 1 plus z. Let us say somebody say that omega 0 e to the power z by 1 plus z over 1 plus z. You can use any kind of crazy thing. It will automatically take this guy over here and it will give you the solution, and you can find, and it is absolutely fast. Over here I am using the c, speed of light in terms of kilometer per second, sorry, kilometer per hour. It's kilometer per second, kilometer per hour, yeah. Now I am using my mu model. Mu model is just m is equal to 5 log of 10 and dl plus 25 and so on. This is my parameters. This is the mu value. Just first of all, I am just making a kind of matrix, column matrix, and then over here I am solving my ODE. Lambda t is just for that. This is the time variable or z variable. Equation is over here that I have three variables, and y column, it will just say that, okay, you just store in y0, y1, and y2. It will store as an array all the data points. Just do it up to 0 to 3, because z is equal to 0 to 3, because when I have data sets, this data set is up to 0 to 2.26, so 3 is enough. It is the initial conditions. All the equations require the initial condition OD0 corresponding to the first equation. So you have to understand the order, because over here you have already defined your EQD, so the order must be in same way, H0, and 0 is again DL. All right, now T evaluate that, okay, where you want to evaluate it. I say that, okay, I have the Z data, but in Z data you will find that if you will see 0.01, again there will be 0.01, so I need some unique points, otherwise it will not work. So unique points, and then method I'm using is Range 45. Obtain the DL solution only, because again it starts from 0, 1 to EQDL. This is for H and this is for DL solution. So this is the second place solution of second, and then interpolate it, because I can just interpolate it and I can just fetch the solutions. So over here what is happening is that you can just put Z over here, Z. So if you just give all the data sets that you have already found out from the data, you can just plug this data and you will find the array of mu value, return my mu value. Once you have defined it, once you have found the mu model, then you define the chi-square. So this chi-square is the data minus theory and then error, which is your covariance matrix. Difference you have to take. Alright, this is also called residual. I am just transposing it. Now I am doing the dot product. This is called the vectorization of dot product. If you will use the for loop, again it will be extremely slow. So you have to use the vectorization method. It will be extremely fast, because this is kind of a NumPy optimized, and NumPy is already written in C. So this is incredibly fast. So what I am going to do is that covariance matrix times the difference. First do this one, this section, and then once you got the result, then take the dot product of this transpose and the resultant one and just give me chi-square. And then I have to use what are my priors. In MCMC it will generate some random value, and sometimes what happens is that if you want to generate H0 for some kind of thing, it will generate negative values too. For an example, OD0, it can also take let us say OD0 is generating 2, it can also pick -2, -3. But again, it's a machine, it doesn't know. It's kind of, producing some random numbers. I have to constrain, I have to tell it that, okay, no, no, no. You cannot just produce any random numbers. So what it says that when the MCMC is taking some kind of value, it will first go over here and it will just check this condition. If it is not meeting this condition, it will just say that, okay, you should not use this value. Go back and again produce another one. So in this way, what it will does that it will only pick those value which is fall in this region, otherwise it will discard it. And return 0 it measure when it is, once it is done, it is now will say that, okay, fine, everything is correct. And then we have to define the log probability. I am saying that, okay, log prior, because the function is over here, parameters, all right. And if prior is equal to minus of infinity, if any of the priors is returning this negative infinity, go back. Otherwise just says the return minus infinity. All right, so this is the condition. Go back to EMCEE, again fetch another value. If its condition is passed that, okay, nothing infinity you have got, now what you have to do is that mu, calculate the mu from the model. You have just invoked get data and the parameters that you have already found out from the MCMC. And then if in any particular value from the mu will get infinity, return infinity, again go back to MCMC. But everything is passed, you can just put the chi-square value. Chi-square is over here, and then you have minus 0.5. So mu Sn from the data, mu from the theory, inverse covariance is the covariance matrix. Return minus 0.5 and so on. Now I have defined my AIC and BIC because these are the statistics thing. You can calculate DIC, whatever the statistics thing you can. And then you have, for the MCMC part, we are defining what are my n walkers. What are my dimensional parameters? Because I am using 3 parameterization, so there is 3. N iteration is 100. You have to must use 10,000 at least to get a good plot. Now this is the random uniform. It means it's giving us some kind of random number. So this is kind of thing that, okay, fine, I'm trying to give me value between these things, but again it will give you any value. It is just no use. If you will not defining this one, then you will not going to give this one, you will not going to get a good result or at all any result. All right, now with the pool processing, I am processing, and from here sampler, I want to sample with the EMCEE, and then I say that, okay, run the EMCEE using the initial position and iteration, and then progress bar has to be true. And then once you are done with this thing, obtain the chains, and then I'm going to flat true. Initially I'm going to discard some kind of chains and thinning by 2%. Whatever the run, you can just thinning it, because again I say that after each and after 10 iterations, forget about it what you have done. Okay, so this is again important in order to get a very good result. So this is the MCMC run that I have optimized with 100 iterations and 30 30 walkers. And you can see the iteration with 7.59 when I'm using my 7 cores, means that 7 CPU. All right, with the parallelization I'm using 7 CPU, and you can see that log likelihood also I am plotting, and AIC value is about 2749. If you will see the paper, you will get that it's about 1703 or something 1603. So it is very near. If I'm using 10,000, I will get near to this point. All right, and you can see over here that these are the something. All right, so again, but if I am optimize it using just only one CPU, I got 12.11 iteration per second. So for 10,000 run, it will be taking maybe 15 minutes or 30 minutes. If I'm using 200, now you can see that the speed has already improved. It is taking 15 seconds for only 200 iterations. All right, so as you are increasing the number of iterations, the speed will also increases, and depending on the number of CPU or the system, again it will boost. Now it says that for the corner plot it is not having the enough data, so you have to again make the iteration up to 10,000. All right, so here I have run it for 10k iterations, and you can see that omega d is 0.61. So you can just say that omega m0 is equal to 1 minus omega d0. All right, h0 I've got this one, and omega 0 I have not considered omega 0 to be minus 1. So here I got minus 0.758. So it is in the quintessence kind of range. All right, so here you can get the good plot. So I will just take, for the publication purpose, I will take 20k or maybe 30k with, let us say, 50 n walkers. All right, so once it is done, I got the AIC value is very close to 763, and then BIC value is 779. Now using this one, I can also use different models and compare it, that what could be the AIC value, and I can just find the difference of AIC using LambdaCDM model. So for this, if omega is not small omega is not, or w is not -1, then you get this one. If you are using lambda CDM, omega becomes -1 and you will get different values. All right. Code. All right. And I am sharing this code in my GitHub repo. You can find it. The link is in description box. And this is the whole thing. And then I'm using my WSL to run this code. So you can see over here in front of you that again, as I have increases the 200 iterations, then this is the result that you are getting, 5.57, 5.49. So if you are not using the optimized code, it is giving you this kind of result. But again, I am telling you that this is huge. People are using integral, and they are, in order to fit the model, it is taking for 20,000, 10,000 huge amount of time. All right, somebody people are also considering that, okay, I have to take some workstations or maybe some supercomputers. No, I'm just saying that you have to just use your optimization, use your brain to make things little bit optimize with the code. All right, you just cannot start with head on. You cannot just apply the brute force. All right. So now if I am showing you that, okay, how it is running with the lambda CDM, which is my optimized one, you can see the speed. So 9.9, 10, it will again increase for 200 runs. All right. So it's kind of very interesting that if you just optimize, I will also optimize a more to get too much speed. So that is the interesting thing. And you have to whenever you are writing some code, you have to mind it that, okay, what kind of algorithm that you are writing. You are not over calculating something, or if you're writing some kind of code, maybe it is repeating itself. So you have to avoid those things. All right. So I guess this video is useful to you, and if it is useful, please share to your friends and your colleagues. And so I'm just sharing you the thank you. So this is Adamina Cap signing out. Thank you so much.